All right, so this is part two to volumes of solids with known cross sections. You've seen part one. It should have looked something like this. We filled this out from the handout by Mark Sparks. Went over a pyramid example possibly as well in this previous lesson that you've seen. So here is part two. In this section we have a region R here that's bounded by these two lines. So we have a sine of pi x, that's the upper right here, sine of pi x, looks like this, with a period length of 2 there, and an intercept of 0. We also have y equals x cubed minus 4x, and that's the bottom one here. So I'll just highlight that, and that's part of, would be a cubic function that would look something like this, okay? So we have the two regions there, and this are the two lines bounding this region. So what this part says here now is we're going to use what we know about cross sections, and we're going to find the volume of the solids that would be formed by the cross sections, which are the shapes indicated below here. So we've done some work in the first video here where we've actually figured out, and that was from the previous. Now let me just go back here and show you what we did. So this work right here, okay? So if we're talking about rectangles, or if we're talking about right triangles, or we're talking about equilateral triangles, we do have the integrals already prepared and set up. So this is from the first video. So right now what we're going to do is we're just going to apply this now. So cross sections, these cross sections now are equilateral triangles. So it would be kind of like this. So this drawing is not going to be real good. But the drawing is going to look like this, okay? So here's one cross section. Here's a, now it's going to go kind of up in the air like this, okay? And here's another one. That one's going to go up in the air like this. And they're equilateral triangles. So however long this is, the distance between these two, that's how high this one is going to be, okay? So again, not very great drawing, but if it was on the level like this, you know, you'd have triangles like this, and then you'd have bigger triangles and so on. Okay, so you kind of get this. So equilateral triangles, anyways, coming from this region. So the volume here is going to be expressed as, and you remember from the previous what we had. Yeah, remember from the previous page here, equilateral. It's this one here. It's the root 3/4. And so this is the expression of the area, and we're going to put it in integral form here, and then we're going to calculate that. So this is going to be root 3/4 times the integral. Now we're going to go from 0 to 2, okay, because that's where they intercept again. So this region is bound between 0 and 2 there. And we're looking for f of x minus f of x sort of thing. So we've got the upper function is sine of pi x, isn't it? Sine of pi x. Minus the lower function there is x cubed minus 4x. So we're actually subtracting that x cubed minus 4x. Okay. And then we're going to square this, the x. All right, so that's what that looks like, and of course we could simplify this in here by distributing that negative sign and so on. Now you don't have to expand anything, okay? And in this type of question, if they ask you to just write the integral representing the areas of these combined cross sections, then you'd be done. If they ask you to find the volume of the solids formed, find the volume of the solid, then you're going to have to actually evaluate this integral. And right now, I wouldn't expect you to do this by hand. So what we're going to do is we're going to do this on the graphing calculator. So if you have a graphing calculator or a graphing technology, then what we're going to do is we're going to use that. So what I would suggest we do is to plug in the root 3/4 times this all squared and graph it, and then we'll calculate the integral that way. So I'll just pause the video here, and I'm going to type that in so I can show you what it looks like, okay? Okay, so as you can see, I've got this I've got this typed into the calculator. You got to be careful with your brackets and stuff, but we're gonna graph, not the integral part, okay? But we're gonna graph the root 3 over 4 times sine of pi x minus x cubed plus 4x. I just simplified this, all squared, okay? Get the same number, right number of brackets and everything. I know it's a bit complicated. But when you graph it, okay, you'll graph it here now, and then you should be able to see that it looks like this. And I've already calculated the integral, so I'll show you how to do that. Okay, but let's go back here. Oh, okay. Anyways, it's this crazy looking graph like this. Now, what you want to do is you want to calculate the integral. Once you've got it graphed, hit second function trace, and then you're going to go down to number 7 here, right? Find the integral. And lower limit's going to ask you for a lower limit, and we want to go from 0 to 2 for this function that we've typed in. So 0 to 2, and then it will calculate the limit for you, and it'll fill in this space like you see here, and it'll give you the value of the integral down here. So 4.32 is correct. That's the volume. So the volume is 4.32 units, okay? Units cubed, I guess. Okay, 4.32. Okay, so that's the first one. That's equilateral triangles. So now we're going to move on to semicircles. Oh, semicircles, no problem. So we still have these the width here, okay, in between the functions, but now we have semicircles like this. It's a little bit easier to draw, maybe. So you can see these are kind of like piling on top of each other, right? Anyways, so we're going to form some kind of solid with semicircles like this now, and they're going to be stacked closely together, right? So how does that look? Well, this volume is going to be, and we already figured out what the integral for cross sections of semicircles look like. And again, I'll bring you back to the previous lesson here, and here we've got the area is pi over 8 f of x minus g of x all squared, or this integral right here. So we're just going to copy this down from that work that we did yesterday, or the previous lesson. So this looks like this, pi over 8 of the integral from 0 to 2, of course. And we're going to go sine pi x minus, and I'll just simplify this time. Get rid of some brackets there, all squared dx. Okay. Now, remember, we've done this work before, so the only difference really here is this root 3 over 4. That's the constant that gives us the, the triangle part, the equilateral triangle. This is the constant here that you're going to multiply this integral by, because notice it's the very same. And that's the constant that's going to give us the area that is represented in the semicircle. Okay? All right. And we went through all that, how to determine that before. So if you do the same thing on your calculator, you should get 3.918 cubic units there for volume. Okay. All right, there is another way that you can do this other than graphing it first. So you would have on your calculator a function integral action, okay, a function on your calculator, and that's going to be here. So look at this, math, and you go all the way down, finint, okay, function integral. Now, if you hit that, it's a bit complicated what you got to do. You got to do that function, and then you have to type in carefully with the right number of brackets. I had to try a couple times for the calculator to understand what I was saying. But you type in this, your pi over 8 times sine of pi x minus x cubed plus 4x. You see how I have it written out there? Okay? All squared. And then you got to do a couple special things. You got to hit the comma here, okay? Comma x. So you have to say it's basically, this is like the dx, okay? Integral, this is dx, all right? So comma x. And then you got to type in your limits of integration in order for it to find a definite, a number here, value. So you got to do comma 0, your lower limit of integration, comma 2, your upper. And you hit enter, and you'll see that you get the same number as you would get if you graphed it. Okay, so this is option number 2. If you have a TI graphing calculator, for sure, I would encourage you to experiment and with other technologies as well, whatever you have there. So let's keep going. A cross-section of isosceles right triangles. Okay, well, we've done equilaterals, we've done semicircles. Now we're going to do, right triangles. Of course, they'll look something like this. We have our x, and then we have a right triangle, right? X with a right triangle, and so on. So a right triangle, not equilateral. We have a 90-degree in there. So that one's going to look something like this. I'll speed it up just a bit here for you. So it's going to be volume, 1/2, okay? Area of a triangle, remember the 1/2 base times height. So 1/2 into, times the integral from 0 to 2 of, you guessed it, sine pi x minus x cubed plus 4x all squared dx, okay? And so this comes from our, the area of a triangle. And for this one, you should get volume should be 4.989 or so cubic units. Okay. All right. I'm going to get you to pause the video now and do this one, D. Do by yourself. And I'm going to get you to pause your video, and then once you play it again, I'll show you the answer. Okay, hopefully you've had a chance to try that. Now, this is actually probably the easiest one because it doesn't have a constant in front at all. It's just simply your base length squared, right? So from 0 to 2, there's no constant out in front. And it's simply sine of pi x, minus x cubed plus 4x all squared dx. And that volume should be 9.978 cubic units. Okay, we're getting close to being done this part of the section now. Cross sections are rectangles whose height is twice the length of the base. Okay, so that's interesting. The height is twice the length of the base. So if we have a base like this, we have a height that's twice as tall. So these are really, really tall rectangles, okay? Really tall rectangles. And in order to understand this, possibly might be a good idea to write something like this out. So if we have our, let's say our f of x minus g of x, okay? Top function minus the bottom function. Or maybe I should write that straight up and down here for you, okay? So here's our, right, looks something like this, right? So if that's f of x minus g of x, then the height is going to be double that. This is going to be 2 f of x minus g of x, okay? All right. So if we're gonna find this area of this, it's going to be what? It's going to be f of x minus g of x times 2 times f of x minus g of x. Now that's not 3, we're not adding them. It's not 3 f of x minus g of x's. We're multiplying them, okay? But what we can do is we can simplify this area as 2 times this f of x minus g of x all squared, because we are multiplying this times itself over here, okay? So if that's the case, then what's that integral going to look like? The integral is going to look like, the volume is going to be, got a little ahead of myself there, leave myself some more room, but it's going to be 2 times the integral from 0 to 2 of, you guessed it, f of x minus g of x all squared, with a 2 in front there. So yeah, I would encourage you to draw a picture, make sure that everything matches up with what the wording there. So volume, again, punch this into your calculator. You should get 19.957, and that's going to be, of course, all of these rectangles with all of these varying lengths of bases, all of them added up together. Okay, so finally we have one left here. What does this one say? Cross sections are rectangles whose height is 1/3 the length of the base. So yeah, we have a situation where if this is the base, then the height is quite short, right? It's very short. This one was twice as tall, but this one's very short. So we've got some short, stubby rectangles there. So the area is going to be straight up. Area is going to be equal to, it's going to be 1/3 of f of x minus g of x squared. So we still have f of x minus g of x here, and we have 1/3 of f of x minus g of x here. So there you go. Integral. Volume looks like 1/3. Integral from 0 to 2 of f of x minus g of x squared d of x. And that volume is going to be far less. It's going to be 3.326 units cubed. All right, so that's video part 2, using a region, an area, and then just building some cross sections. So that's part 2. What I want you to do now is to look at day 63 homework. Credit to Mark Sparks for this material we're using today. It's really awesome. I encourage you to check out all of his stuff. Mark Sparks, AP Calculus, complete course. It's really excellent. So I'd like you to do the day 63 homework from that course. All right, so here's the homework questions. You should have a printout of this. Should be you can print this out from my website, or maybe on your Google Classroom if you're in my class. But here are the questions. Number 3 and 4 might be a little bit tricky if I remember correctly. That's pi of x too, by the way. Yeah, we might need to talk a little bit more about this 3 and 4, but there's 5 and 6, 7, and 8. Awesome. Okay, so that's part 2 of the cross-sectional volumes.